Hi, my dear. Thank you, Jimmy. How are you? My dear, continually Chapter 9, Flow in Closed Channels Under Pressure. Part B, Flow through Simple Pipe System. Steady flow through pipes. All the application of steady flow of fluids in pipes can be solved by using the principle of conservation energy Bernoulli equation. The simple way for solving such problems can be done by drawing both the two energy lines such as total head line GHL or total energy line GEL and head gradient line HGL, which can be assessed to calculate both head and mean velocity of water flow at any pipe extension section. Look, my dear, hydraulic gradient line HGL is the line which gives the sum of pressure head P divided by gamma and the position head Z of a flowing fluid in a pipe with respect to reference or data line. Take in consideration that the pressure head P divided by gamma would be positive if the hydraulic gradient line is placed above the pipe center line, while P negative if it is laid under pipe center line and equal to 0 when crossing. Anyhow, total head line or total energy line GHL or GEL is the line which gives sum of hydraulic gradient line and the velocity head or kinetic head of a flowing fluid in a pipe with respect to reference or datum line, which is equal to Z plus P divided by gamma plus B squared divided by 2G. My dear, total head line THL or total engine line TEL can be obtained also by joining the tops of all vertical ordinates showing the sum of pressure head B divided by gamma and the velocity head B squared divided by 2G from the center of pipe, which is equal B divided by gamma plus B squared divided by 2G, such as position head Z will be equal to 0 at scale. Take into consideration that these two representative lines, hydraulic gradient line and total energy line, are parallel, while the vertical difference between them equal to the kinetic or velocity at all the flowing cross section of the pipe. Flow through simple pipe systems. The first one, flow through a horizontal pipe between two condensate head tanks as shown in the enclosed figure. By applying Bernoulli's equation between points 1 and 2, hence you can calculate the head losses between the 2 points as shown in the enclosed equation. Look, my dear, by applying Bernoulli's equation between points 3 and 4, hence you can calculate the head losses between the 2 points and also the velocity of flow as illustrated in the enclosed equation. Flow through a horizontal pipe at the side of condensate head tank as shown in the enclosed figure. My dear, by applying Bernoulli's equation between points 1 and 3, hence you can calculate the head losses between the 2 points and also the velocity of flow as illustrated in the enclosed equation. Continually, by applying Bernoulli's equation between points 2 and 3, hence you can calculate the head losses between the 2 points and also the velocity of flow as shown in the enclosed equation. Flow through a nozzle fitted to a horizontal pipe at the side of condensate tank as shown in the enclosed figure. By the same way, by applying Bernoulli's equation between points 2 and 3, hence you can calculate the head velocity between the 2 points and also the velocity of flow as shown in the enclosed equation. The rest of calculation, the head losses and the velocity of flow through a nozzle fitted to a horizontal pipe at the side of condensate tank. Flow through a slope pipe at the side of condensate tank as shown in the enclosed figure. Look, my dear, by applying Bernoulli's equation between points 1 and 3 as this case, hence you can calculate the head velocity between the 2 points and also the velocity of flow as shown in the enclosed equation. Continually, by applying Bernoulli's equation between points 2 and 3, hence you can calculate the head velocity between the 2 points as this case and also the velocity of flow as shown in front of you. Flow through a cracking pipe between 2 condensate tanks is very important as shown in the enclosed figure. My dear, by applying the same way and applying Bernoulli's equation between points 1 and 2, hence you can calculate the head losses between the 2 points and also the velocity of flow as shown in the enclosed equation. Follow it by yourself, my dear. It is so easy and clear. Flow through a pipe has a vertical flow part between 2 condensate tanks as shown in the enclosed figure. Flow through a pipe has a valve between 2 condensate tanks as shown in the enclosed figure. By applying Bernoulli's equation between points 1 and 2, hence you can calculate the head losses between the 2 points and also the velocity of flow as illustrated in front of you. The rest of calculation, the velocity of flow through a pipe has a valve between 2 condensate tanks. Look, my dear, by yourself. It is so clear and easy. Look, my dear, there are 2 cases concerning valves such as maybe fully opening or partially opening. Take into consideration start, flow, angle, gauge, check, or butterfly valve. Moreover, its opening condition must get into consideration, such as 3/4, 1/2, and or 1/4 opening. Anyhow, secondary losses reference to the valve type and opening condition can be calculated easily as equivalent lengths in pipe diameter, as shown in the previous table and figure. Flow through a pipe has a pump between 2 condensate tanks. It has 2 cases as its case, pumping from a lower level to upper level, or pumping from an upper level to lower level, as shown in the enclosed figure. The rest of calculations head losses a case of pumping fluid from a lower level to upper. Look, my dear, by yourself. Pumping fluid from an upper level to lower level, as shown in the enclosed figure, and also calculation the head losses as this case. Flow through a siphon between 2 large tanks. Really, siphon is a long bent pipe usually using to transfer liquid from an upper level reservoir to another one at a lower level when the two reservoirs are separated by any obstacle in between. Fluid can't flow up the siphon summit unless priming it at first because its summit level is above the fluid level in the upper tank, and hence the pressure at the summit be negative at this case. Take care and precaution must take in consideration to let the negative pressure at summit be smaller than the vapor pressure of transferring fluid to avoid the cavitation phenomena and also to achieve the full running at summit section. Figure showing flow through a siphon connected between two large tanks, and its summit level is higher than the fluid level in the upper tank by a distance y, as shown in front of you. My dear, by the same way, and applying Bernoulli equation between points 1 and 3, hence you can calculate the head losses between the 2 points and also the velocity of flow as shown in front of you. Goodbye.